So today I'm going to talk about dynamic potential games. This is a joint work with my previous student Athira Prasad and my current PhD student Parthasarathi. So the outline of the talk is as follows. So first I'll briefly talk about the preliminaries and the problem statement. Then focus on feedback potential difference games. And then the sufficient conditions were associated with the existence of feedback potential differential games, then conclusions and future work. So to start with, first I focus on basic static games. So a static non-cooperative game in normal form is given by this triplet, where n denotes a set of players. So if you have any questions or something, if something is not clear, please feel free to interrupt me during the talk, and I'll be more than happy to answer any questions. So n denotes a set of players, and SI is a strategy of player I, and S denotes a joint strategy set. So where capital S is the strategy set of player I. Phi I is basically the cost function of player I, and I use the notation minus I for the set which excludes player I. Okay. So a strategy profile is a Nash equilibrium for the game. If for each player this condition holds true, that means no player I does not have an incentive to deviate from the strategy SI star when other players use their Nash equilibrium strategy. So basically here, here the computation of Nash equilibrium involves solving n simultaneous minimization problems. So we ask the following question, and since at least researchers in game theory have asked the following question: is there a function phi such that the minimizer of this function is also a Nash equilibrium for the game? In the sense, can I solve a Nash equilibrium problem because this is a fixed point problem? So is it possible to obtain the Nash equilibrium through an optimization problem? That's a question we are after. So this problem was studied extensively in the static games community. So this set of problems were studied first, at least in the literature, they direct to the work of Rosenthal. So where Rosenthal was interested in identifying the class of games which admit pure strategy Nash equilibria. Then in oligopoly games, as the title of the paper suggests, what does an oligopoly maximize? So this is published in the International Journal of Industrial Economics. So Margaret Strait was looking at ways to obtain the equilibrium through an optimization problem. So so here, especially the functions whose minimizers are provide Nash equilibria, actually those functions are called as fictitious functions in this paper. But a complete theory was provided by Monroe and Shapley, and they call these games as potential games, and they also talk about different variations of them as ordinal potential game, exact potential game, and so on. And the geometrically, these geometrical characterization of at least decomposition of the non-zero sum games into potential games and something called as a potential part and harmonic part and so on was studied by Kondogan in mathematics of operations. So, but what is a potential game? So a potential game is actually a strategic form game is called an exact potential game if there exists a function such that for every player I and a set of strategies of other players, the following condition holds true. So what this condition says is, if other players fix their strategies at S minus I, and player I varies his strategies from X to Y, then the payoff difference should be same as the payoff difference that's obtained through this function phi. Then this function is called as a potential for the game G. And a differential formulation of this is basically the partial derivative of phi I with respect to player I strategy should be same as the partial derivative of this function phi with player I strategy. So, and this has to hold true for all players. So from this, it's kind of clear that the necessary conditions associated with the Nash equilibrium problem are coinciding with the necessary conditions associated with the minimization of function phi. So that's where one can actually say that the local minimizers of this function can provide feedback, Nash equilibrium of a static. So that's the intuition. But this is true only when this function is known a priori. Suppose if I don't have this function, is there a way to characterize a static game as a potential? So for that, one has to look into multivariable calculus. So here we are looking at a slightly, so basically this can be, this object can be seen as variation of function in certain direction. Yes. So so that means I can collect all these for all the players, and I can form a vector in the joint strategy space, and that has an interpretation of a gradient. Yeah. So then we are looking at if there exists some function such that the gradient of this function is exactly same as the vector field. Yeah. So this is a classic result from multivariable calculus, which says that let phi omega be a convex open subset in Rn. Let F be a vector field with continuous derivatives defined over omega. Then the following conditions on F are equivalent. That is, there exists a scalar potential function such that this vector field is exactly same as a gradient of this function. Okay. These conditions are all equivalent in the sense A means B, B means C, and so on. So then, for the existence of this scalar function, there must be some conditions on this vector field, and those conditions are basically, as we can immediately recognize, these are called as exactness conditions, where the cross derivative of the ith component with the jth component of omega should be same as the partial of jth component of F with the ith component of omega. And this has to be true for all the indices. Basically, what we are saying is the Jacobian of this vector field should be symmetric. Okay, that's actually the condition. If that is true, then it is possible actually to construct this scalar function through a line integral in the sense. And so here I'm interested in computing the potential at a point omega, okay, W, but I have to fix, I have to start somewhere in this set omega. So any arbitrary curve that actually joins between the fixed point A and the variable point omega. So the difference in that potential can be obtained through an arbitrary path that connects these 2 points. That's what it means. And this integral is actually path independent. Okay, whenever F satisfies these exactness conditions. Okay, that's the idea. So to just give a simple example of interpretation of what is a conservative vector field. So we have a vector field yx, that is in x direction it takes the magnitude y, and in y direction it takes the magnitude of x. Then we can use basically the exactness conditions, and this is actually exact, and it can be shown that this is a gradient of this function. But whereas if I take this vector field is not exact. This is not a conservative vector field. So basically, a conservative vector field does not swirl around too much, in the sense it won't, the swirling does not happen in a conservative vector field. That's the intuition. Okay. So using this idea, Monder actually provides a condition for the existence of a potential function for a given strategic form game. So here, the payoff functions must satisfy these exactness conditions, then it's possible to construct a potential for that game. Okay, here the idea is I just have to set these FIs to be the partials of the payoff functions of player I with the player I's own Bayesian variable. So I can stack all those partials, and that is a vector field. And that vector field has, if I use exactness conditions on that vector field, then I basically these are those conditions. Yeah. So then we can construct a potential function. So that's, but as you can clearly see, this is not unique. It depends on the initial point alpha that I choose. That's a fixed point. So in some sense, I can get a family of potential functions here. Okay, so that's basically roughly the idea of potential functions in a static game. So the idea, to summarize, basically it is motivated by the idea that computation of an equilibrium is solved as an optimization problem. So the local minimizers of the potential function provide Nash equilibria, and also especially in finite games, if the game is a potential, it's a potential game, then a pure strategy Nash equilibrium exists for that game. Yeah, and people have studied these and shown that the best response dynamics also converges in a potential game, and congestion games, which are studied in networks, they're shown to be potential games. And properties and applications are widely studied even in the engineering literature, computer science, and so on. Yeah. But the focus of this work is on dynamic potential games. So it's a dynamic extension.
Hi, Vishwa, I have a question.
Yes.
So
yes.
if the exactness condition is satisfied, then we can always find a potential function.
Yes.
Okay. Thank you.
That's right. Yeah. So just to briefly summarize what a dynamic game is. So here I take the most simple dynamic game, which is given in which is discrete time framework. But of course, the theory can work for differential games or even other variations of dynamic games. So I assume N to be the player set, K to be the set of time instants. Xk is a state vector at time instant K. Uk is a control of player I, and UKI is basically the control set of player I. This bold UK is basically the joint controls of players at time instant K, and U tilde is basically the joint strategy profile of all the players. So, and the dynamics here is that is the state evolution is influenced by the control actions of all the players, yeah, and it's given by this equation. And the cost functional of player I is given by this equation. And here I assume that f and gk, I mean, these functions are twice continuously differentiable in their arguments. So here, so basically now, as we have seen in a static framework, a potential game is basically a way of computing an equilibrium as an optimization problem. So a natural question in a dynamic game context would be, is it possible to obtain the Nash equilibrium through an optimal control problem? But in a dynamic setting, the outcomes, that is the Nash equilibria, are information dependent. So that means with open loop information structure, players use strategies which are functions of the initial state and time. In feedback information structure, the strategies are functions of time and the observation of the state at time K. Yeah. So we have basically two types of Nash equilibria depending upon the information structure. So when we talk about a potential game, so we have to also talk about, I mean, in a dynamic game context, it doesn't make sense unless we emphasize the information structure. So that means an open loop potential game, a potential dynamic game, or here is a differential game, difference game, means that there must be an optimal control problem. Solution of that optimal control problem provides an open loop Nash equilibrium. And when we say potential feedback potential differential game, means there must be an optimal control problem that provides solution of that problem, provides feedback Nash equilibrium. So in some sense, a dynamic potential game admits two different associated optimal control problems that we can immediately infer from the information structure, the importance of information structure in a dynamic game. Yeah? So yes.
Vishwa, I have a question. So in a static game, we said that, okay, we can find a potential function.
Yeah.
So the minima or maxima of this potential function, is it unique?
Yes. So because as you can see, the local minimizers of the potential function actually provide the Nash.
Okay.
Yeah, you can have multiple as well.
Okay.
Because
always it will happen that the minimizer of the potential function will give you a Nash equilibrium for the game problem.
Yes. Yes.
Okay.
Yes. Yeah. Because it's through this, you can immediately infer from it. Yeah. So some literature survey on dynamic potential games. So here it's an inverse problem in the sense we are trying to see the necessary conditions associated with the computation of equilibrium, and we are talking about an optimal control problem, existence of an optimal control problem. So I mean, similar. I mean, work of. In some sense, work of Descartes also looks at similar problem where he is trying. I mean, he tries to look at a system of second order difference equations, basically are Euler equations of a calculus of variations problem. So it's also an inverse problem actually. So yeah. And again, the work of Slade has initial ideas on open loop and feedback potential dynamic games. And Dragon et al. Look at Hamiltonian potential games, which are formulated in open loop framework. Zazo et al. Is a difference games with inequality constraints, again in open loop framework. Mazalov et al. In potential linear-quadratic difference games, again in open loop framework. And Gonzalez, Sanchez, and Hernandez Lama to look at identify classes of discrete time stochastic games which admit potential functions. So here these are quite restrictive class of games. They looked at both open loop and feedback information structures. In the work of Gonzalez and Sanchez, Hernandez Lama, there is a survey paper on static and dynamic potential games. And in a differential games context, but in open loop framework, again from Hernandez Lama and his collaborators. So in some sense, the majority of the existing works cover open loop framework, but not on the feedback framework. So that is one of the motivation for our research, at least. So this is just, we started looking at these problems, thinking that not much work has been done in the feedback framework. So basically now, what is a feedback potential difference game? A feedback potential difference game is basically a non-zero sum difference game is FPDG if there exists an optimal control problem such that the solution of this problem provides a feedback Nash equilibrium for the difference game. Yeah. So here, this is a OCP. So here, basically, the optimal solution of this optimal control problem should coincide with the feedback Nash equilibrium of the original game. Here, since it's an inverse problem, we could have different cost functions of the OCP, optimal control problem, and the dynamics also can be different. But in this work, we choose the dynamics to be same as the dynamics in the game. Yeah, but in fact, it can be different as well. Yeah. So just briefly summarize the computation associated with feedback.
Vishwa, it's not clear to me the last comment you make. Can you repeat it, please, on this F bar?
Yeah, so here the dynamics in the optimal control problem, this need not coincide with the dynamics in the game.
Okay, I got it.
Yeah,
I got it.
Yeah,
Thank you.
Yeah,
Thank you.
Yeah, because it's an inverse problem, it can be very different. So here in our work, we chose that the dynamical evolution is also same because it has some kind of physical interpretation, how players actually are interacting with the environment. So we can keep it to be the same.
I have a related question.
Yes.
So, so you are saying that assuming the same dynamics as the original problem does not affect the equilibrium.
Oh yeah, no.
So what would be the reason for taking a different dynamics if it doesn't affect the equilibrium?
Yeah, see, this is a inverse problem. So that means if I'm only looking for a minimum of one function, but I can have a family of functions where, for which the minimum can be same, right?
Yes.
So I'm just restricting that family. That's all. That's all I'm doing by taking fk bar to be as fk. That's all. Did I answer your question, sir?
Yes. Thanks.
Yeah. Okay. So just to see, basically in a feedback Nash equilibrium is obtained by solving the Bellman equation, that is the dynamic programming equation. So where Vki is the value function of each player. But here the main important thing in the formulation of feedback Nash equilibrium is so at every time step we're actually solving a static game where the payoff of player I is basically the instantaneous payoff plus the cost to go accumulator from stage k plus, from k plus 1 till the terminal time, right? Yeah. So in some sense, we have a static game at every stage k. So players actually play a static game at every stage k where the payoffs of players are these. Yeah. And the feedback Nash equilibrium at stage k, in fact, E is the Nash equilibrium for this static game. So that's ideal. Because I'm repeating this because we'll use the same concept. We'll use the static game notions of static potential game ideas here to give the sufficient conditions. Yeah. So, and for an optimal control problem, this is the value function. And again here, when we use dynamic programming at every stage k, I'm actually solving an optimization problem, and the optimal control at evaluated, this is the entire control profile, but at stage k, this minimizes this cost function. So now once we have these notions, I can immediately give, it's possible to give a condition for a potential game, the dynamic potential game with feedback information structure. So here we have reduced this entire dynamic problem as static problems through the dynamic programming equations at every stage k. So we can immediately use the static game conditions that the function is actually a potential for game, that is static game at stage k. If and only if for every I, for a player I, this condition holds true. Yeah. Further, the strategy profile obtained as minimizer of this objective function, that is this cost function, is a feedback Nash equilibrium for the difference game. Okay, so thing is, this result assumes that we already know this function phi, phi, and we also need to know the forms of the value functions here, right? So in some sense, yeah, this result is true, but applicability is for the problems to verify it can be difficult because it assumes that we know the functional forms of value functions. So, but now the question is, if the optimal control problem is not available a priori, so this is exactly the parallel question where the potential function is not available, then one can use the exactness conditions, right, on the static game. So do we have similar conditions also in a dynamic context, in a dynamic setting? Yes, here now we so here at every time step, at every time step, I have actually a function of u and x. Yeah. So I can now take the partial of phi with u, and also I have to take a partial of phi with x, because I have two variables here. And so I can actually generate the vector field f with x and with u, where fx is the partial of playwrights payoff with x. There is a reason it's only one. I'll get back to that. And the partial of phi with respect to u, that is phi with respect to ui, and I collect all for all the players as fku at times. Yeah. But here I cannot have partial of player 2's payoff with x and so on, because if I construct, if I string all those partials, I'm going to get a vector field which is of dimension n times capital N plus m, but the domain is only Rn plus m. Yeah, so that means it almost says that I have more vectors I'm generating when I cannot. So the only way I can generate as many vectors as possible in that many directions is by this condition. Yeah, so that is that means the partial of playwrights payoff with respect to x must be same for all the players. Yeah, with respect to x. Is this clear? If there are questions, please let me know. But that's the idea here. In a dynamic case, this is what we get when we don't know the optimal control problem a priori. So then we use these exactness conditions, and we can actually compute the payoffs associated with the optimal control problem at every stage. In principle, we can do that. But here, the sufficient conditions are quite restrictive, because here x is not a decision variable, it is a parameter. And the vector field that we have here is on both x and u. So the piecewise continuously differentiable path that I'm going to take, it should be only, so xk must be fixed actually. So along that path, xk is fixed. So it is actually a line passing through xk, but this line is the entire Rm basically. Yeah. But we feel these sufficient conditions are very restrictive, but most of the existing literature, we see that these exactness conditions are present in most of the works. But we believe that these are very restrictive. To show this with a counter, with an example. So I assume that the playwrights payoff is of this form, which is quadratic. If I don't have an optimal control problem, that is here it's a static problem, but here I make it as parametric with x to explain the I would say how restrictive these conditions are. Yeah. So then we see that if I impose, these conditions would require that A1, A2 should be same, B1, B2 same, C1, C2 should be same, and F1 and F2 to be the same. So these are game parameters. Yeah. So then, of course, I can actually get the following potential function. But if I already know that, say, for instance, I fix my class of potential functions to be quadratic and say of this form, then if I use theorem 1, this is the only restriction I'm going to impose. All of them, there are no restrictions on the parameters of the game parameters. So this demonstrates that these exactness conditions are very restrictive, because here x is also treated as a decision variable, but x is a parameter. It is not a decision. So now it gives some kind of an idea that maybe it is better to look at classes of games where we already have some idea about the functional forms of the value functions. And maybe it's possible to generate basically sufficient conditions or enlarge the classes of different games. So what motivated us is to look at linear quadratic class of difference games, where maybe it is possible to obtain some sufficient conditions for the existence of feedback potential difference games, and also maybe it is possible also to construct, so whenever the optimal control problem is not available, we should be able to construct at least a family of optimal control problems which provide the feedback Nash equilibrium. So here in linear quadratic games, the advantage is we know the value function, how the function forms of value functions and so on. So here, when I say a linear quadratic difference game, it's identified with the parameters, that is A, B1, B2. Here I restrict attention to two-player case, but an n-player extension should not be that difficult. So, and the parameters of the objective functions are RKI and QKI. So basically these are the game parameters. And the optimal control problem parameters are RK bar and QK bar. Here I don't assume RK to be, I assume only to be symmetric. No positive semi-definiteness, only symmetric. That's only assumption on R matrices and Q matrices. So, but here we are now interested in problem 1, that is, given the game and as well as an optimal control, that means here game parameters as well as the optimal control problem parameters. When can we say that the solution of this optimal control problem provides a feedback Nash equilibrium of this linear quadratic difference game? Yeah, so that's the first question. That means here I already have the data of the game as well as the optimal control. The second question is, I don't have the optimal control problem. I mean, it's not available for me. Then I only have the game problem, that is game parameters are available. When can I say that this game is a potential feedback potential difference game? And once I know it is, it admits a potential game structure, can I construct a family of optimal control problems using the game parameters? So that's the question we are after. So these are the two problems we are interested in looking at. So to just review the feedback Nash equilibrium and also the optimal solution of in a linear quadratic framework. So we have the feedback Nash equilibrium actually has the following structure. So here I assume the value function is quadratic. Then the feedback Nash equilibrium, there is a feedback Nash equilibrium profile is given by this formula, and theta k is given by this matrix, where this means the one block of RK1. This means 2 block of RK2. This is 1 2 block of RK1 and 2 1 block of RK2. So that's the meaning. It's a submatrix. And here these HI matrices are obtained by the recursive, basically coupled Riccati difference equations, which are backwards in time. So these are initialized at QKI associated with the terminal cost, and one can obtain this backwards in time. For once game parameters are given, then I can compute all these matrices. But here I assume that these parameters also additionally satisfy these conditions. This means the feedback Nash equilibrium that I'm going to get is unique, because I want this uniqueness also to exactly say that the optimal control problem solution indeed is actually the feedback Nash equilibrium. So I enforce, these are the conditions that I assume on the problem parameters. So these are the conditions, and all these matrices we can compute in linear quadratic games. So now for the optimal control problem, so here the parameters are with bars, yes. So I can also compute all these parameters, and where theta, I assume that this is also strictly convex. Yeah, that is, this matrix is strictly convex. Okay, so now once the game and the optimal control problems are known, I want to know basically when exactly this optimal control, the solution of this optimal control problem indeed is the feedback Nash equilibrium of the game. This is basically, we use theorem 1, and the conditions are, that is both the game as well as the optimal control problems parameters have to satisfy these conditions jointly. So basically, let the parameters satisfy the following conditions. Then the game is a feedback, potential game with the optimal control problem, that is LQ OCP as an associated optimal control problem. Here, associated optimal control problem means that the solution of this provides a feedback Nash equilibrium of this game. So that's what it is. The sketch of the proof is basically we apply. Here we at every stage K, I have a static game. And at every stage K, I have this optimization problem, and we use the conditions from theorem 1 to get these conditions. So that's pretty much it.
Vishwa, I have a question. So
yes.
These results can only be derived if you know the form of the value function.
But in the linear quadratic case, I already know the form of the value.
Yes. So these results are obtained for LQDG. You were able to obtain these results because you know the form of the value function, right?
Yes.
Okay.
Yeah, that's true. So now the question is, suppose I don't have the optimal control problem parameters, but only I have game parameters. Then if I use the exactness conditions from theorem 2, so these are the conditions. But here I call the first condition as XX with XU and UU, so these conditions. So basically we already saw an example where this condition is too restrictive. Then at least in the linear quadratic case, can we relax this and use only these two conditions to actually come up with some sufficient conditions? Yes, so that's what we are looking at here. And because since I am relaxing this condition, so I cannot use, we just cannot use the line integral approach of conservative vector fields to get the potential functions. So we have to use a different line of argument to show that if only XU and UU, these two conditions are actually sufficient to say that this game admits a potential game structure. So that's the next result. So here we cannot use now the conservative vector field approach because once this condition is relaxed, the vector field is no longer conservative. So now we have the next result, which says that if the game parameters at time instant K satisfy this condition, this is XU condition. And from time instance K minus 1 to 1, if the game parameters satisfy this condition, this is UU condition and this XU condition. And at time instance 0, if the game parameters satisfy these conditions. So here there is no condition on Q matrices, so they are free. We are free to choose them. This is a UU condition. Then the game actually admits a potential game structure. So here the proof, we found it a little tricky in the sense we used induction, backward induction to prove this. So here the sketch of the proof is as follows. At terminal time K, I set, here the idea is we can actually construct an optimal control problem using the game parameters, and then once we already construct an optimal control problem using the game parameters such that the solution of this optimal control problem is same as the feedback Nash equilibrium, then we are done. So we construct this backwards in time. So we set the terminal cost parameter of the game, that is QK bar, as the terminal cost parameter associated with player 1. This implies this condition holds true. Yeah. Then now we have to set the parameter RK minus 1. Yeah. So, but the idea here is basically RK at any time K can be set as follows, where HK +1 is computed before in the previous step. Yeah. So now once RK bar is fixed, I can actually fix QK bar. So this is how it is done. So the optimal control problem is actually constructed this way. So our claim is that the feedback Nash equilibrium will be same, exactly same. That is, the Nash equilibrium at stage K is exactly same as the optimal solution at stage K of the optimal control problem we have been so we constructed so far. So that's the idea here. So basically here I set QK at terminal, that is QK bar at terminal stage. Now we set RK -1 at K -1. So then this particular choice immediately, I mean, using this choice, we can show that the Nash equilibrium at stage K -1 is exactly same as the optimal solution at stage K -1. So now once this is shown, we go ahead and set the parameter for the game. So we are constructing the game now, optimal. Yeah. So sorry, constructing the optimal control problem. So that this the optimal control problem parameter QK -1 bar is set as follows. Since I already computed this, I already set this parameter in the before. Yes. So this is already set. So then we can actually set this parameter and so on. So we can actually do this process. So basically, the proof here uses a different approach. In fact, we can relax that XX condition. We use only XU and UU. Those two sufficient conditions are enough to show that. I mean, to show that this game admits a feedback potential game structure. So here. In the proof, like we constructed only one particular optimal control problem, but this particular optimal control problem has a feature that the optimal cost to go is exactly same as in the optimal control problem is same as the equilibrium cost to go of player 1. So that's how it is constructed. Yeah, but in fact, we can generate a family of optimal control problems because the condition that we require at every stage is this condition. This is what is being used. Yeah, this condition, this condition. So then a question, a natural question is, why should I choose? I mean, HK bar is obtained. I mean, through QK bar actually. So right. So that's what we do next, in the sense we exploit that freedom because the condition that I require is this condition, not a more strict condition. In the proof, we used a strict condition to get one particular choice, but in fact, this is what is required. So we can use this, I mean, there is a lot more freedom here. So we can exploit that to generate a larger class of optimal control problems. That's the idea here. So in fact, here we say that, yeah, let the problem parameters satisfy the conditions in theorem T3. Assume the set of optimal control problems characterized by these parameters satisfy the following conditions. So that is, now I'm not fixing QK bar as same as player 1's matrix, but I choose QK bar such that this condition holds. Yeah. And but say the RK bar is fixed as the same as we fixed in the proof, but QK bar is fixed always such that this condition holds true. So then we can immediately, following the same lines of the proof, we can show that the so constructed optimal control problem indeed provides a feedback Nash equilibrium of the game. And this set is always non-empty because we already constructed one particular solution in the previous proof, right? So that means that this choice always exists. So this set is non-empty. So now to talk about the sufficiency of this condition, in the sense, can we do a little better by relaxing even the other sufficient condition UX? At the moment, we don't know. But we have an example that says that this condition probably is not required. Yeah, so here we see for a two-stage game, so these are the game parameters, then the feedback Nash equilibrium is computed as follows. Now we consider a optimal control problem with these parameters. Then we see that this condition is I mean, even if this condition is violated, so this optimal control problem actually has same solution. I mean, is exactly same as a feedback Nash equilibrium. So that means there, of course, yeah, these are sufficient conditions. So we can always have optimal control problems. I mean, even if the game does not admit these sufficient conditions, we can still have optimal control problems which provide feedback Nash equilibrium of the game. So, in symmetric games, the computation of feedback Nash equilibrium is considerably of less complexity because of the number of equations required for computation are low. So then a natural question that comes to mind would be whether symmetric games naturally admit feedback potential game structures. That means for symmetric games, difference games, can we say that there always exists an optimal control problem where the solution of that optimal control problem provides feedback Nash equilibrium of the game? And actually, indeed, it is true that all symmetric linear quadratic difference games admit a feedback potential game structure. So we can show that. Basically, using the same lines of the proof, we can show that. So that's basically about the theory part of the work. If you have any questions, please let me know before I go to the numerical simulations.
Vishwa, I have a question about the definition of the feedback potential difference game. So in the definition, there is no potential. So, I mean, it is like, it looks like a classical difference game, but
yes.
Yeah. So what is the, I mean, the reason why you call it potential game in the definition you gave at the slide? So can you explain this?
Yeah, sure. So I think the name is called because of the static, I would say, but the idea is inspired from the static game framework where we solve an optimization problem to obtain a Nash equilibrium. So those games are called as potential games. So in a dynamic setting, that word is just used, I think, to reflect the same principle, that feedback Nash equilibrium or open loop Nash equilibrium can be obtained by solving an optimal control problem. So that's
okay.
Yeah.
Okay, thank you.
Yeah.
Because I mean, this is an optimal control problem, right? That's why it's a potential game, because this OCP is like not a game problem; it's a control problem, right?
Yes. Yeah.
And also, by definition, all symmetric games are potential. I mean, different symmetric games, linear quadratic. They all are.
Yes, all of them. Yeah.
Yeah. Thank you.
I mean, we can show that basically.
Yeah.
Okay, so we have a numerical illustration, which is actually a very simplified form of a network flow game that's presented in Zazu's work. So here we have two players. Each player is interested in sending some data from source. Player 1 is interested in sending data from source 1 to the destination T1. Source player 2 through source 2 to destination T2, target C. And they use a joint relay. Basically, the idea of relay here is if I'm sending some information, the information can get attenuated. So in between, I have these devices which actually amplify and send it to, basically it's a repeated amplified versions. Yeah. To account for the noise and so on, or attenuation and so on. Yeah. But these, since both the players use this relay, so the battery level of the relay node at time k evolves according to the following difference equation. In the sense, the battery gets depleted if it's used more. If the transmission rate is more, the battery gets depleted fast. And of course, the battery has a natural depreciation factor. So this is the evolution of the battery level in the relay node. And each player has basically transmission rate dependent utility in the sense is this term. In the sense, I send more data, I derive more utility. And the players also have interest in conserving the battery level, because once the battery dies, of course, they cannot transmit. So both of them have interest in keeping the level high. So now this can be written as a cost problem. Yeah. So, and I assume all these parameters to be positive scalars and so on. And so that's a game here. So, but this is not in the standard form, LQ form. So we can do some transformation of the game to recast as a standard form. So then for this problem, basically, we can use the conditions that are presented in theorem. Yeah. So then we see that at stage 2, the game parameters should satisfy these conditions. Then we can actually construct all the optimal control problems in the game parameters for which the solution of this optimal control problem is indeed a feedback Nash equilibrium of the game. So all the optimal control problems are basically given by the following game parameters. Here Q2 is any arbitrary variable, and this S is basically the class of symmetric matrices. So Q0 is any 2 cross 2 symmetric matrix. Yeah. So this is basically the family of all optimal control problems. The solution of these problems will provide a feedback Nash. So all these problems have the same optimal solution. That's the thing. Yeah, that's the point I want. So now, in a symmetric case, basically we can compare now between the open loop Nash equilibrium and the feedback Nash equilibrium and the optimal control problems associated with the open loop Nash equilibrium and the feedback Nash equilibrium. So here in the open loop information structure means the players only have knowledge about the initial battery level. Here they can design in a feedback case, they can strategize based on the observation of the current battery level. Yeah. So we can actually construct the optimal control problem which provides solution of this problem provides the open loop Nash equilibrium. And here, this is the optimal control problem. The solution of this optimal control problem provides a feedback Nash. So in some sense, a dynamic game can admit 2 associated optimal control problems depending upon the information structure. So this is just an illustration of this idea. So so basically, the conclusions in the sense, so we have we looked at dynamic potential games with feedback information structure. So this is not it's not well studied in the literature. We provided sufficient conditions for the existence of feedback potential games, and for linear quadratic games, we could get some sharper results in the sense we could construct optimal control problems from the game parameters, and also a family of optimal control problems from the game parameters only, and the solutions of this family will have only the same optimal solution. That indeed is a feedback Nash equilibrium of the original game. So for future work, we still want to analyze, at least we want to obtain even sharper results by relaxing the sufficient condition with Ux basically. And in so far, we only studied the interior solutions. We have not looked at the solutions where we can have boundary solutions. So we did not impose any inequality constraints and so on. And we also are interested in seeing these problems in a continuous time framework. So that's pretty much it.